Here we must first use our imaginations a little to try and understand where the nuclei and atoms that surround us came from, our entire material world. We will now encounter astrophysical phenomena, which should answer the question of how nuclei and atoms originated. This is the question of how the material world came into being, how the universe came into being. It is very often said that the universe originated in the Big Bang. But what is the Big Bang? One thing we do know is when it happened, which was a long time ago. 13.7 billion years have passed since then. Somehow we are here, and now we will talk about how it all was born and originated, and what the Big Bang was. But here I must mention that this is only a model, and we will see whether this model is testable in an experiment or not. In general, it does not describe the cause or conditions under which this Big Bang occurred, but rather everything that happened after it. They say that at the beginning, there was the so-called Planck era. That is, there was a very small size in which a very large energy, a very large mass was concentrated, and this led to an explosion. I don't really like the words big and small. If I say infinitely small size and infinitely large mass, or infinitely high density, then I will not add anything more, because we will still need to introduce some physical quantities from which to start. Therefore, it is necessary to introduce some initial conditions. The initial conditions introduced by Planck looks like this. Planck said in 1906 that all theories that we create, fundamental theories, universal gravitation, electromagnetism, and so on, are ultimately tested by an experiment. All of these theories are calibrated by some constants that allow us to understand this world. There are only 5 of these constants, the so-called fundamental constants. I have written 4 of them here. This is the speed of light, quite a clear value. This is the gravitational constant. We know the law of universal gravitation, that the force that acts on 2 bodies and attracts them to one another is nothing more than m sub 1 multiplied by m sub 2 divided by r squared, which is the distance between them, and there is a constant g in front of them. That is the gravitational constant. However, Planck's constant says that if we have a quantum, there is connection between the quantum energy and the frequency. Well, we write it as E equals hv. This h is Planck's constant. And finally, there is the Boltzmann constant, which connects energy to temperature. We use the concept of temperature, which depends on energy, and this dependence is regulated by the Boltzmann constant. Now, let's try to get new values from these fundamental quantities, the Planck values, which we will then apply in order to understand what happened in the Planck era. In this way, we are then essentially exploiting Maxwell's equation, electromagnetism. We're talking about the law of universal gravitation. We're talking about quantum mechanics, which is Max Planck, and we're talking about thermodynamics and statistics, which is Boltzmann. From these fundamental laws, we will now draw out the units that, if we're talking about length, then I will only use those units that I show, h by g divided by c cubed, which turns out to be 10 to the power of minus 35 meters long. Please note that 10 to the power of minus 35 meters still makes sense, but less than 10 to minus 35 meters no longer makes sense, because there is no length less than 10 to minus 35 meters. Well, 10 to minus 35 meters is the Planck length, and all distances can now be measured to the Sun or anywhere else with this new value, the Planck length. The volume will be a cube of this size. It will be 10 to the power of minus 105 cubic meters, respectively. How much substance by weight can you stick into this volume? The Planck mass says, again, using only those constants, 10 to minus 8 kilograms, micrograms. And time, we have to divide the length of time by the speed of light. And then we get 10 to minus 44 seconds. Again, please note that anything more than 10 to minus 44 seconds can be counted, but that anything less than 10 to minus 44 seconds cannot be measured. And finally, the Planck temperature, which was 10 to the power of 32 Kelvin, an enormous temperature which cannot be higher. And now we will stick in here all of these numbers that we have just obtained, and we will see that it was a small volume heated to 10 to the power of 32 Kelvin. The density was 10 to the power of 97 kilograms per cubic meter. This is 10 to the power of minus 43 seconds, 43 seconds. And the radius of the universe was 10 to the power of minus 35 meters. These were the initial conditions. But how were they formed, these initial conditions? We know that there are 4 types of interactions: electromagnetic, weak interaction, strong interaction, and gravitation. All 4 interactions took place when the initial substance was in this state. The strongest interaction was gravitational, which squeezed the substance to such a small size, causing the unification of all of the interactions. As you will see now, everything scattered after the unification, and today's theorists dream of recreating the theory of the grand unification, which they're talking about, and there are many preliminary developments for this. Today, we're using the standard model, which includes electromagnetic, weak and strong interactions, but does not consider gravitational ones. This model was accepted until recently, when gravitational waves were first discovered, as predicted by Einstein 100 years ago.